Hi, welcome to yet another interesting lesson on gases. So, in our previous video, we talked about the van der Waals equation, which describes the behavior of real gases. Okay, in this video, in this lesson, we're going to look at ideal gas laws. Okay, so the equation that we are going to describe here, those that pertain to ideal gases. Okay, so at the end of this lesson, we're going to answer this question that is here. This is a 2019 paper 1, and this was question 4B. So we are doing this lesson so that we can be able to answer questions such as this one here. All right, so ideal gases are just hypothetical gases that obey the ideal gas laws. All right, so we are going to delve into the ideal gas laws. But examples of those hypothetical gases would be hydrogen molecule, okay, the diatomic molecule of it, the helium element or gas, the nitrogen gas, the diatomic molecule of it, the oxygen diatomic molecule, and even argon, to mention just but a few. So these are just hypothetically considered to be ideal gases, but they can also deviate from ideal behavior once they're exposed to extreme limits, such as very high temperature or pressure. So these equations are so fundamental in physics and chemistry, and they describe the behavior of ideal gases under various conditions. All right, so what we are going to be talking about here is the pressure multiplied by volume is equal to number of moles multiplied by the gas constant and the temperature. Right, so wherever we're going to mention this temperature, we should picture it in Kelvin, because this Kelvin is the standard unit for temperature. Temperature's standard unit is not a Celsius or Fahrenheit, but it's the Kelvin. The absolute zero temperature scale is the one that we use here. So as you can look at this formula, it's quite different from the van der Waals equation that we discussed in that video, because in it we found variables such as a, small a, and b. All right, a, that was the van der Waals constant, and b also the van der Waals constant, one referring to the size of the particles, the other one referring to the force of the force of attraction between molecules. Okay, so this is it. So we are dealing with pressure multiplied by volume, equating it to number of moles, gas constant, and temperature. So I want us to know that P is just the pressure of the gas. Okay, the pressure of the gas. V is the volume of the gas. Okay, N is the number of moles. Okay, R is the gas constant, and T is the temperature in Kelvin. All right, so this is what we are basically going to focus on, this equation here, as we look at these ideal gases. All right, so we've got to note that no real gas perfectly fits the ideal gas model. So all these, as we mentioned, all these gases here are just but considered to be ideal gases under certain conditions. Otherwise, they're also capable of deviating from the behavior of the ideal gases. So I want us to look at these three gas laws. Okay, the Boyle's law, the Charles law, and Joseph Gay Lussac's law here. So This P is for pressure, so that is initial pressure, and this V is for volume, so that is initial volume, then final pressure and final volume. In this expression, temperature is constant. Temperature is kept constant. Temperature is not changing. All right. So Boyle's law states that the pressure of a given mass of a gas at constant temperature varies inverse proportionally to its volume. All right. Great. So the other one is Charles' law. Under Charles' law, we have the initial volume, we have the initial temperature, we have the final volume, and the final temperature. What's constant here is the pressure. All right. So Charles' law states that at constant pressure, the volume of a given mass of a gas varies directly proportionally to its temperature in Kelvin, of course. All right. So volume varies directly proportionally to temperature in Kelvin, provided pressure is kept constant. Joseph Gay Lussac's law states that the pressure, remember this is pressure, this is temperature, initial, final. All right. And what's kept constant here is the volume. So Gay Lussac's law states that at constant volume, the pressure of a given mass of a gas is directly proportional to its temperature. And the temperature is in Kelvin, of course. Always remember that. Always remember that. So, having understood what we have here, I'm going to expose you to this equation here, this expression, and that is P1 V1 is equal to P2 V2 over T2 over T1. Interesting. Very, very interesting. So I want us to note something here. Okay. So this expression combines all the three of these equations here. All right. So we are going to note that if we get the upper part here, what we have is Boyle's law. All right. And if we get this part as well as this part here, what we get is Charles' law. All right. If we get the remaining part, allow me to use red again. If we get this remaining part here and this remaining part here, what we are going to have is Gay Lussac's law. All right. So in short, this expression combines all of these gas laws and their equations. Right. So let me just write them independently. So when you say for Boyle's law, so Boyle's law gives us pressure, volume is equal to pressure, volume. All right. So final pressure multiplied by, initial pressure, multiplied by initial volume equated to final pressure multiplied by final volume. Okay, so this is Boyle's law. Then for Charles' law, another Charles' law, we get to discover that we have the volume and the temperature, okay, equated to the volume 2 and the temperature 2. Right. So temperature in Kelvin, of course, T in Kelvin. Always remember the absolute zero, the standard temperature unit. All right, so the volume, so this is initial volume. V1 is initial volume, V2 is final volume, T1 is initial temperature, T2 is final temperature. Then Gay Lussac's law, Charles Gay Lussac's law. What do we have? We have the pressure over the temperature equated to pressure final over temperature final. All right, so P pressure, T temperature. All right, so I want to take you back to that question that we have, because that question can be answered using one of these three equations. So the data itself gives us the idea. The use of information provided in that question gives us the idea of what we should use. So let's quickly go back. It reads, figure B 4.1 shows a cylinder containing a gas of volume 5 centimeters cubic at a pressure of 100 kilopascal. So the piston is pushed to half the original volume at the same temperature. So in this case, temperature is kept constant. All right, at the same temperature is kept constant. Then what do we have? We have this volume, and we have half of it as another volume. Then we have this pressure that we are given here. All right, so we can solve this using Boyle's law. Here we are asked, A is asking us to state Boyle's law, and then after stating Boyle's law, we are using the same Boyle's law because we have pressure and what? And volume. Okay, we have pressure and volume, so we can solve this. I'll read through again, then it will be up to you to try. When you try, let me have your answer in the comment section, either YouTube or Facebook or LinkedIn, wherever you come across this. Try it, then let me see your answer. I'll be very happy to interact with you. I'm just going to read it once again in order to help you collect clear data. So this figure shows a cylinder containing a gas of volume, that's the volume, that's the initial volume, at the pressure of, that's the initial pressure. The piston is pushed to half the original volume, so which means the half of 5, which is 2.5, is actually V2. Okay, V1 is 5 here, V2 is 2.5, which is half of 5. All right, the units of course carried. Then the initial pressure P1 is actually equal to this one. Okay, is actually equal to 100 kilopascal. So what we are asked to calculate here on B, we are asked to say calculate the gas pressure in the cylinder in this figure. So calculate P2. All right, calculate P2. So if we had to observe clearly, what we are going to use is this formula. We are going to have P1 V1 is equal to P2 V2. This is what's going to give us the answer, the correct answer in that on that question. So try it. That's 2019. That's 2019. Let me just bring it here for you to see it in case you struggle to find the past paper. Okay, so here's the question for you. Thank you very much for joining. It's Pearson, the science teacher. Let's learn together. So this uh, lesson unveiled a lot of uh, facts about ideal gases, and this is one of the perfect example we can use in this lesson. I'm really anticipating your answers. Please, 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 let me see you try this. Thank you very much.